In this video, I'm going to explain what is VSEPR theory and going to go through how to draw the basic molecular shapes or electron pair geometry, linear, trigonal, planar, tetrahedral, trigonal bipyramidal, and octahedral, and going to guide you how to predict and explain the shapes of molecule and bond angles in a given species. Molecular shape. Molecular shape of a molecule is derived from the valence shell electron pair VSEPR theory. In VSEPR theory, it stated that electron pairs around central atom repel one another and try to arrange themselves as far apart as possible in order to minimize the repulsion. And the repulsion between the electron pairs basically can be divided into lone pair repulsion, lone pair bonding pair repulsion, and also bonding pair repulsion. And the lone pair repulsion is the strongest, followed by lone pair bonding pair repulsion, and the bonding pair repulsion around the central atom being the weakest type of repulsion. And to determine molecular shape of a molecule, basically we just need to follow through 4 steps. Step number 1, we need to draw the Lewis structure first. Then in step number 2, we determine total electron pairs around the central atom and determine the electron pair geometry. And in step number 3, we then can draw the molecular shape and state the molecular shape based on the electron pair geometry. And in step number 4, we then can determine the type of repulsion around the central atom and also the bond angle in the molecule. Now we move on to look at basic molecular shapes, or also being called as basic molecular geometry or electron pair geometry. In SK015 Matriculations Chemistry syllabus, there are 5 basic molecular shapes that we are going to cover, and the first one is linear. So for basic molecular shape linear, basically this class is called as AX2. A represents the central atom and X represents the terminal atoms. And in linear basic molecular shape involve 0 lone pair and 2 bonding pairs around the central atom. Therefore, there are 2 total electron pairs around the central atom, and that 2 electron pair around the central atom both are bonding pairs. And according to the VSEPR theory, these 2 bonding pairs, they need to stay as far apart as possible in order to minimize the repulsion. Therefore, they will stay basically 180 degree apart. And this 180 degree apart is the bond angle for molecule with AX2 class adopting linear electron pair geometry and having molecular shape linear. And the type of repulsions involved, since both are bonding pair, therefore the type of repulsions involved will be the 2 bonding pairs repel each other equally. And this is the example of the 3D model of linear molecular shape, where the 2 bonding pairs they repel each other equally and therefore staying 180 degree apart from one another. And this 180 degree again is the bond angle for molecule with linear shape and having electron pair geometry linear. The second basic molecular shapes or electron pair geometry that we are going to look at is trigonal planar. For trigonal planar, basically the molecule is from the AX3 class, where A is the central atom and the X is the terminal atoms. And then for the AX3 class, basically there is 0 lone pair and 3 bonding pairs around the central atom, and therefore total 3 electron pairs around the central atom. And these 3 electron pairs, the bonding pairs, they need to stay as far apart as possible from one another. So how to stay as far apart as possible from one another? Basically, they need to stay 120 degree apart from one another. And this 120 degree basically is the bond angle for the molecule with molecular shape trigonal planar and electron pair geometry trigonal planar and having 3 bonding pairs only around the central atom. And this is the 3D molecule of molecule with trigonal planar molecular shape and electron pair geometry also trigonal planar. And we can see that these 3 bonding pair around the central atom forming a triangle. and this triangle basically lying on the plane. Therefore, the name of this electron pair geometry and molecular shape is called trigonal planar, representing a triangle lying on a plane. And since these are all three bonding pairs, therefore only bonding pair repulsions involved, and these three bonding pairs repel each other equally to give bond angle 120 degrees. The third basic molecular shape or electron pair geometry that we are going to look at is from the class AX4. A represents central atom, X represents the terminal atom. So from the class AX4, basically the molecule have 0 lone pair and 4 bonding pairs around the central atom to give total 4 electron pairs around the central atom, and therefore the basic molecular shape or electron pair geometry is tetrahedral. So how to draw tetrahedral? So central atom A. So this bonding pair pointing out, and then this one is at the side. And then can you see that this bonding pair is pointing towards us? And when pointing towards us, in the drawing, we need to use solid wedge. And the bond that is pointing away from us, we need to use dash wedge. Be careful when draw tetrahedral. These three bonding pair must draw pointing downwards, because the basic molecular shape having these three bonding pair pointing downwards, and then these two bonding pair, they are on the same side. The solid wedge and the dash wedge must be on the same side. In basic molecular shape tetrahedral involve 4 bonding pairs. And these 4 bonding pairs need to stay as far apart as possible to minimize the repulsion, and that will give bond angle equal to 109.5. And the type of repulsions involved is only bonding pair repulsion, and that 4 bonding pairs will repel equally to give the molecular shape tetrahedral based on the electron pair geometry or basic molecular shape tetrahedral due to having 4 bonding pairs only around the central atom. The fourth basic molecular shape or electron pair geometry that I'm going to go through is trigonal bipyramidal with the class AX5. Again, A represents central atom and the X represents the terminal atom. For the class AX5, basically there is no lone pair but 5 bonding pairs around the central atom, giving total 5 electron pairs around the central atom. And the basic molecular shape or electron pair geometry that is adopted is called trigonal bipyramidal. Basically, these 5 bonding pairs, they need to stay as far apart as possible to minimize the repulsions. So the basic molecular shape that it is going to adopt is going to be having 2 bonding pair in the axial plane. So these 2 bonding pair in the axial plane, and then another 3 on the equatorial plane. So on the equatorial plane, we have this bonding pair, and then this bonding pair pointing towards us. So we use solid wedge to represent the bond pointing towards us. And then another bond pointing away from us. So we use dash wedge to represent the bond pointing away from us. And the bond in the axial plane is 90 degrees apart from the bond in the equatorial plane. So that gives the first bond angle 90 degrees. So it's between the axial and the equatorial plane. The angle between the 2 bonding pair, one in the axial plane and another one in the equatorial plane. And then the bonding pair on the equatorial plane, basically these 3 are the bonding pair on the equatorial plane. They are 120 degrees apart from one another. And that gives the second bond angle for trigonal bipyramidal molecular shape with electron pair geometry, trigonal bipyramidal, and 5 bonding pairs, and total 5 electron pairs around the central atom. And the type of repulsions involved is only bonding pair repulsion, and these 5 bonding pairs repel each other equally to give the bond angle 90 degrees between the axial and equatorial plane, and 120 degrees between the bonding pair lying on the equatorial plane. The last basic molecular shape or electron pair geometry that we are going to look at is from the class AX6. So again, A represents central atom and the X represent the terminal atoms. In the AX6 class, basically having 0 lone pair and 6 bonding pairs around central atom, therefore total 6 electron pairs around the central atom, and the electron pair geometry therefore is octahedral. So how to draw octahedral electron pair geometry? So the central atom A, one bond on the top and another one at the bottom. And then this bond is pointing towards us, so we use solid wedge to represent it. And this bond is pointing towards us as well, so we use solid wedge to represent it. And then this bond is pointing away from us, we use dash wedge to represent it. And this bond also pointing away from us, we use dash wedge to represent it. And these 6 bonding pairs, basically they are staying as far apart as possible from one another to minimize the repulsion. And that give the angle between the bonding pair as 90 degrees. And therefore the bond angle in octahedral molecular shape, electron pair geometry octahedral with 6 bonding pairs only around the central atom is 90 degrees. And the type of repulsions involved would be bonding pair repulsions only, because only 6 bonding pairs involved, and these 6 bonding pairs repel each other equally to give the molecular shape octahedral based on the electron pair geometry octahedral due to having 6 bonding pairs around the central atom. Now we move on to look at the examples on how to determine the molecular shape of a molecule. In example 1, we want to determine the molecular shape of carbon dioxide and state the bond angle in carbon dioxide. To do this, basically there are 4 steps to follow through. First, we need to draw the Lewis structure, and step number 2, we determine the electron pair geometry or basic molecular shape. And then we draw the molecular shape, and step number 4, we determine the type of repulsion and also the bond angle. So step number 1, draw the Lewis structure. To draw the Lewis structure, first we determine the total number of valence electrons of all the atoms involved. So here we have one carbon having 4 valence electrons. So electron from carbon is therefore 4, and oxygen valence electron 6. There are 2 oxygen in carbon dioxide, therefore times 2 to give 12 electrons from oxygen, and therefore the total valence electron involved is 16 electrons. Then we draw the skeletal structure for carbon dioxide. So carbon being less electronegative be the central atom, and oxygen are the terminal atoms. By drawing the skeletal structure for carbon dioxide, we have drawn 4 electrons, so therefore minus 4 to give us 12 electrons remain. Then we need to measure the terminal atoms, oxygen, octet, by putting another 6 electrons around each of the oxygen. By making the terminal atom oxygen's octet, we have drawn 12 electrons, so no more electron left. So no more electron left, then we need to move on to look at the central atom. So carbon, central atom, not yet octet. So how to make it octet? By using the lone pair on the terminal atom, making one multiple bond, and the carbon still not yet octet, so we need to use another lone pair on the oxygen to make another multiple bond. Then the central atom octet, and therefore this is the Lewis structure for carbon dioxide. And in step number 2, we need to determine the electron pair geometry. To determine the electron pair geometry, first we need to determine the total number of electron pairs around the central atom. To determine that, we need to know the number of lone pair around the central atom. Around the central atom carbon, there is no lone pair, so lone pair 0. How about the bonding pair? So basically, there are 1, 2. So 2 bonding pairs around the central atom carbon. Even though this is double bond, we are still considered as 1 bonding pair, 1 group of electrons. So therefore, 1 bonding pair and another one, another double bond, another bonding pair. And that gives total electron pair around central carbon equal to 2. By having total electron pair around central atom 2, That means that the electron pair geometry is linear. So linear, still remember, must have central atom A, middle, and then the two bonding pair lying 180 degrees apart from one another. So this is basically is the linear electron pair geometry. And to draw the molecular shape of the carbon dioxide, it must based on the electron pair geometry. Therefore, carbon central atom must be at the middle, and then the first bonding pair and second bonding pair lying 180 apart from one another. So this is the molecular shape of carbon dioxide, and this molecular shape is called linear shape. And step number 4, we want to determine the type of repulsion. So only two bonding pairs involved. Therefore, in carbon dioxide, only two bonding pairs repel one another equally. So only bonding pair repulsions involved, and two bonding pairs repel each other equally. And that gives bond angle of 180 degrees. In example 2, we want to determine the molecular shape of aluminum chloride and then set the bond angle in aluminum chloride. Again, to do this, 4 steps to follow through. Step number 1, we draw the Lewis structure for aluminum chloride. To draw the Lewis structure, first we need to determine the total number of valence electron for the atoms involved in aluminum chloride. For aluminum, 3 valence electron, and there is only 1 aluminum in aluminum chloride, so multiply by 1 to give 3 electrons. And chlorine, 7 valence electron. There are 3 chlorine atoms in aluminum chloride, therefore multiply by 3 to give 21 electron, and therefore total valence electron involved is 24 electrons. Then we can draw the skeletal structure for aluminum chloride. Aluminum, being the less electronegative, will be the central atom, and the chlorine be the terminal atoms. By drawing the skeletal structure, we have drawn 6 electrons, and therefore 18 electrons remain. Then we want to make sure the terminal atoms octet by putting another 6 electrons in for each aluminum atom to make the terminal atoms octet. By putting all the 6 electrons in for each of the chlorine atom, we have drawn 18 electrons. So no electrons remain for the central atom. For aluminum chloride, because aluminum as a central atom, it can have incomplete octet. Therefore, this is the Lewis structure for aluminum chloride. Then we can move on to step number 2, determine the electron pair geometry of aluminum chloride. To determine that, first we need to determine how many lone pair around the central atom aluminum. From the Lewis structure, we can see that there is no lone pair around the central atom aluminum. How about the bonding pairs? There are 1, 2, 3. 3 bonding pairs around the central atom aluminum. Therefore, total electron pair around central atom is equal to 3. When the total electron pair around central atom equal to 3, this means that the electron pair geometry adopted by aluminum chloride will be trigonal planar. So trigonal planar, central atom, and then the 3 bonding pair forming a triangle in a plane, like this. And the bonding pair will be 120 degrees apart. So this is the electron pair geometry for trigonal planar. Then in step number 3, we want to draw the molecular shape for aluminum chloride based on the electron pair geometry trigonal planar. So to draw that, aluminum as a central atom and the 3 bonding pair must align like a triangle in a plane like this. And the 3 bonding pairs will repel each other, and to minimize the repulsion, they must be 120 degrees apart from one another. And this molecular shape of aluminum chloride is called trigonal planar, because the three bonding pair arrange themselves like a triangle in a plane. And what type of repulsions involved? Only three bonding pairs, therefore only bonding pair repulsions involved, and that three bonding pairs repel each other equally to give the bond angle equal to 120 degrees. In example 3, we look at how to determine the molecular shape of CCl4 and state the bond angle in CCl4. Again, to do this, we need to follow through the 4 steps. Step number 1, we need to draw the Lewis structure for CCl4. To draw the Lewis structure, first we need to determine the total number of valence electrons in CCl4. In CCl4, involve carbon, one carbon having valence electron 4, therefore 4 electrons from carbon. Chlorine, 7 valence electron. There are 4 chlorine involved, multiplied by 4 to give 28 electrons, and therefore total valence electron involved is 32 electrons. Then we draw the skeletal structure for CCl4, carbon being less electronegative than chlorine be the central atom, Cl be the terminal atoms. By drawing the skeletal structure, we have drawn 8 electrons. Therefore, 24 electrons remain, and then we need to put in the electrons to match the terminal atoms octet. So each of these chlorine, we need to put 6 electrons to match the chlorine octet. By putting 6 electrons on each of the chlorine atoms, we have drawn all the 24 electrons. So no more electrons left to put on the central atom. And carbon, being the central atom, has also achieved octet, and therefore this is the Lewis structure for CCl4. Step number 2 is to determine the electron pair geometry for CCl4. To do that, first we need to ask ourselves how many lone pair present around the central atom carbon. From the Lewis structure, we can see that there is no lone pair around the central atom. And how about the bonding pair? There are 1, 2, 3, 4 bonding pairs around the central atom carbon to give us total electron pair of 4 around the central atom carbon. By having total electron pair 4, it means that the CCl4 having electron pair geometry of tetrahedral. And still remember how to draw the tetrahedral electron pair geometry. So central atom, and then 1 on the top, bonding pair, and another 3 must pointing downwards. 1 coming out pointing towards us, we draw with solid wedge, and another one pointing down away from us, we need to use dash wedge. So this is the electron pair geometry tetrahedral, and step number 3, we need to draw the molecular shape for CCl4 based on the electron pair geometry that we deduced in step number 2. So carbon, the central atom, 1 bonding pair to Cl pointing upwards, another one bonding pair, and 1 bonding pair pointing downwards towards us. We use solid wedge to represent it, and then 1 bonding pair pointing away from us downwards, we use dash wedge. So this is the molecular shape of CCl4 we draw based on the electron pair geometry tetrahedral that we deduced in step number 2. And these 4 bonding pair in CCl4, they repel each other equally, and to minimize the repulsion, they need to be 109.5 degree apart. And in step number 4, we need to determine the type of repulsion in CCl4. Only 4 bonding pairs involved, therefore only bonding pair repulsions, and that 4 bonding pairs repel each other equally to give the bond angle as 109.5 degree in CCl4. In example 4, we look at how to determine the molecular shape of PCl5. Again, follow through the 4 steps. Step number 1, we need to draw the Lewis structure for PCl5. To draw the Lewis structure, first we need to determine the total number of valence electrons involved in PCl5. In PCl5, there is 1 phosphorus with valence electron 5, therefore multiply by 1 to give us 5 electrons from phosphorus. There are 5 chlorine atoms, each chlorine atom having 7 valence electrons, therefore multiply by 5 to give us 35 electrons from chlorine atoms. That gives us total valence electrons of 40 in PCl5. Then we draw the skeletal structure for PCl5. Phosphorus, being less electron negative than chlorine, will be the central atom. By drawing the skeletal structure, we have drawn 10 electrons. Therefore, 30 electrons remain. Then we need to make the terminal atom's chlorine octet. To make the chlorine octet, we need to draw on each 6 more electrons. On each of the chlorine, 6 more electrons. On each of the chlorine, 6 more electrons to make the terminal atom chlorine octet. So on each chlorine atom, 6 electrons to make the chlorine atom terminal atoms octet. By drawing 6 electrons on each of the chlorine, so we have drawn 30 electrons. So no more electron left to put on the central atom. And phosphorus already have 10 electrons around it. So basically, this is the Lewis structure of PCl5. Step number 2, we want to determine the electron pair geometry in PCl5. To do that, first we need to determine how many lone pair around the central atom phosphorus. From the Lewis structure, we can see that there is no lone pair around the phosphorus. How about the bonding pairs? So from the Lewis structure, we can see that there are 1, 2, 3, 4, 5. 5 bonding pairs around central atom phosphorus. And that should give us total electron pair around central atom equal to 5. And by having 5 total electron pair around central atom phosphorus, it means that PCl5 having electron pair geometry of trigonal bipyramidal. And all these 5 bonding pairs, they need to stay as far apart as possible to minimize the repulsions. Therefore, one will be on top, another one at the bottom, and then 3 more will be on the equatorial plane. So one towards us on the equatorial plane, and then one away from us, we need to draw using the dash wedge. And step number 3, we need to determine the molecular shape of PCl5 based on the electron pair geometry that we deduced in step number 2. So phosphorus being the central atom, and then chlorine terminal atom, we must draw it based on the trigonal bipyramidal electron pair geometry that we deduced in step number 2. So on equatorial plane, one bonding pair towards us, another one away from us. Axial and equatorial plane bonding pairs will repel each other and stay 90 degrees apart from one another, and then the 2 bonding pairs on the equatorial plane will stay 120 apart from one another. So step number 4 is to determine the type of repulsions involved in PCl5. Since only 5 bonding pairs involved, therefore only bonding pair repulsions present in PCl5, and these 5 bonding pairs repel each other equally to give bond angle of 90 degrees between the bonding pair on axial plane and equatorial plane, and angle between the bonding pairs on the equatorial plane is 120 degrees apart. Example 5, we are going to determine the molecular shape of SF6, sulfur hexafluoride. Again, to determine the molecular shape of SF6, need to go through the 4 steps. Step number 1 is to draw the Lewis structure of SF6. To draw the Lewis structure, first we need to determine the total number of valence electron of atoms involved. For sulfur, 6 valence electron, there is only one sulfur in SF6, so multiply by 1 to give 6 electron. Fluorine, having 7 valence electron, there are 6 fluorine in SF6, so multiply by 6 to give 42 electron. So total valence electron involved is 48 electrons. Then we draw the skeletal structure of SF6. So sulfur being less electronegative being the central atom. By drawing the skeletal structure, I have drawn 12 electrons, so 36 electrons left. Then I need to put electron on terminal atoms fluorine to make it octet. So each of the fluorine need to place 6 electrons to make the terminal atom fluorine octet. So each fluorine atom, I need to place 6 electrons more to make them octet. So by drawing 6 electrons on each of the fluorine atom, I have drawn all the 36 electrons. So no more electron left to put on the central atom sulfur. So this is the Lewis structure for SF6. After done with step number 1, then we move on to step number 2 to determine the electron pair geometry of SF6. So first we need to determine how many lone pair around the central atom sulfur. So from the Lewis structure, we can see that there is no lone pair around the central atom sulfur. How about the bonding pair? By looking at the Lewis structure, we can see that we have 1, 2, 3, 4, 5, 6. 6 bonding pair around the central atom sulfur. Therefore, total number of electron pair around the central atom sulfur is equal to 6. By having total electron pair equal to 6, that means that SF6 having electron pair geometry of octahedral. So octahedral, how to draw octahedral? Central atom, 1 bonding pair on the top, 1 at the bottom, 2 pointing towards us. So we need to draw using the solid wedge, and then 2 away from us, pointing away from us. So this is octahedral. And step number 3, we need to determine the molecular shape of SF6 based on the electron pair geometry that we deduced in step number 2. So we know that the molecular shape is based on the electron geometry octahedral, so we need to draw the molecular shape based on the octahedral. So sulfur central atom, so 1 bonding pair on top, 1 at the bottom, 2 pointing towards us using solid wedge, another 2 pointing away from us. So this is molecular shape octahedral. To minimize the repulsion, the bonding pairs will stay as far apart as possible to give the bond angle 90 degrees. So what type of repulsions involved? So only bonding pairs involved. Therefore, in step number 4, only bonding pair repulsions involved, and that 6 bonding pairs repel each other equally to give bond angle 90 degrees.